Hey there, and welcome to part 7 of the easy speedrun. So we have another 10 problems. I think these are going to be a little bit more varied than the last few times. So let's begin. You're given a large integer represented by an integer array. Digits are ordered from most significant to least significant. The large integer does not contain any leading zeros. Increment the large integer by 1 and return the array. Okay, so I think we're going to have some kind of something like this. And then 4 digit, or so we're going to have to iterate backwards. So, okay, this one, and then we're going to say res equals I plus cn, okay, yeah, and digits I equals res mod 10, okay, and then if res does not equal to 10, we can return here. Yeah, otherwise we need to say cn equals 1. Okay, I think that's pretty much it, and then if cn we put a 1 in the front, I think, and then we just return. Hopefully that's it. Oh crap. Let's see here. Digits I plus, oh, I need to make this 1 to start off, right? Okay. Okay, cool. Happy number, right now, I'm going to turn numbers happy. Happy number is determined, okay, starting with positive, replace the integer with the sum of its digits, repeat the process until the number equals 1, or it loops endlessly in a cycle which does not include 1. Those numbers which the process ends with 1 are happy. Return true. Okay, so we're going to need to have a visited set to check for duplicates. So while n is, can it ever be 0? No, I don't think so. Okay, so while n is greater than 1, let's just say if n in visited, that means we already seen it. So we return false here. Then we replace the sum of its digits, so we can just make some temporary number, right? So temp equals n, while temp, let's say, maybe. Or do I want to do that? No, I want to do something else, I think. Sure, and then I could have the sum of its digits, right? So sum digits equals 0. Now I could do, well, temp. So sum digits, and then they're squared as well, right? Yeah, okay. So then we need some kind of output. So res equals temp mod 10, that's the last digit, then some digits plus equal res squared, and then temp equals temp divided by 10. Okay, and that should do that, I think, and then we just make n equal to temp, or n equal to some digits in the end, so n equals some digits. Okay, return true here because it's 1. Oh, okay. Hopefully that's right. Jesus. How many? Oh, this F. Okay, we have a infinite loop in some way, so how's that? Oh, right, we need to do one more thing. Now we can add it here. We can add it in either place, actually. But let's add it here. Yeah. There you go. Okay. Okay. Meeting rooms. Given an array of meeting time intervals, interval I, start, end, determine if a person can attend all meetings. Okay, so we have to sort these. So for all these interval questions, we have to sort first. Then all we do is just we check, do they have an intersection? So for I in range, len intervals -1 here, if intervals I1 is greater than intervals I plus 1, 0, return. I'm not sure what it does if it's equal, so we'll just see that. Okay, here we have this again, problem. Okay. Okay. Min cost climbing stairs. Okay, so this is the easiest dynamic programming. Cost, you start at 0, 1, return the min. Okay, so we're going to say, we're just going to use the optimal solution here. It's pretty straightforward. So if n equals, or sorry, if len cost is less than or equal to 2, return max cost. So that's pretty straightforward, I think. Yeah, so with 2, index 1. Okay. Now we just say the first last as we have in house robber. So first last equals cost minus 2, cost minus 1, for I in range. So this is what? Length cost. So this is length cost minus 1, length cost minus 2, so minus 3. Yeah. Then what are we doing here? So for this, we're paying the cost regardless, right, at the step we're at, and then we can either climb 1 or 2. So it's going to be 1 or 2. Okay, so first last equals cost I plus, so if it's these two, then first is going to be cost I plus last. No. Okay, so I think first is cost I plus first. If that's one step, it's actually going to be, no, it's not going to be that. So if we're here, it's going to be the minimum of these two, right? Yeah, I think so. So this is minimum, first, last, I believe. Yeah. And then this is going to be first, return. Hopefully that's right. Yeah, let's see here. Okay, so, oh right, one more thing. Hopefully that fixes it. Okay. Oh, so we got something wrong. Output 100, expected 1. Oh, this should be min. So. Okay. Alright. Climbing stairs. You're climbing a staircase. It's the same kind of question. Each step, you can only take 1 or 2. Okay, so this will be the same thing. So if n equals 1, let's say, return there's only 1. Now otherwise, first, last. So if we're on the last step, so let's think about this. You can either climb 1 or 2 steps. So if n equals 2 steps total, so the last step would be, we're there already, right? So that is 0, and then first is 1. So I think it's 1, 0, right? So now for I in same kind of thing, range. Okay, so now what this would be, so this is, we are already on step 2. Now this is step 1, now we need step 0. Okay, so this is n minus, so this is n minus 1, n minus 2, I think. swan. So first, last equals, so now what is it? So if we have 3 steps, so it's going to be you take 1 step plus the minimum, I believe, or is it no? No, it's just going to be 1 plus the other, right? Yeah. So I think this is going to be first plus last, I think. It's going to be first. Now we return first. Is that right? Dang it. Okay, let's see what this is. So for this case, first last is 1, 0. First is going to be first plus last. I see, so that should be 1. So let's actually draw this out real quick just to help us. So at step 0, we are at something. At step 1, we are at something. At step 2, we're at something. At step 3. Okay, so at step 3, there are no steps. At step 1, there is only one way. Here, there are 2 ways. And here, I think there's 3 ways, right? Yeah, that's what it's saying. So it is the addition, but the problem is it breaks here. So what we want to do is we want to take this case, I think. So this is going to be 2, 1. Yeah. And now we just, so if this is n minus 1, n minus 2, so now it's n minus 3. So hopefully that works. Hard to do this on the fly for sure. Cool. Verifying an alien dictionary. An alien dictionary prize. Order alphabet given a sequence of words. Okay, in the order return true if only the given words are stored lexicographically in the alien language. Words, order. Okay, so what we're going to have to do is we're going to have to check every word. Okay, and then we're going to also have to make a dictionary here so that we're order equals this, let's say, and then for I in range length order. So this is going to be order. Oh, we need to call this something else, right? So this is just call it like language maybe. So we have to say where it is. So language order I equals I. Okay, now we made our dictionary. Now we have to compare every 2 words. Okay, so for, let's just say, that's fine, I in range length words minus 1 because we're comparing every word to the word after. Okay, so first equals words I, second equals words I plus 1. Okay. Now, the way we do this is we go letter by letter, I believe. Yeah, so let's just do, and then the other case we have to think about is, I think, do they have this case? Yeah, here we go. The first 3 app, second string is shorter, according. Okay, so yeah, so the blank character is less than any other character, so that's the other thing. So the first word has to end first, and if the second word, okay, so this is fine. So we can just do, yeah, so we're going to do for j range length first. So if j is greater than or equal to length second, then we are at false. Yeah, because then the first word is longer, which doesn't make sense. Otherwise, if language j comes before language I, we also return false. Otherwise, we just keep checking. We return true here. Hopefully it didn't screw anything up here. Of course. So what do we got? Words I plus 1. Oh, right. So. Okay, if language I. Interesting. So key error 0. How would that happen? if okay, for j in range length first, that should be fine. If j language j, okay, let's just print this real fast. Just to do this. This should be fine. Yeah, so all these letters are in there. So we're never gonna have. Okay, so for j in range, if j is greater than or equal to length second, return false, right? If language j is less than language I. Okay, let's just print. Oh yeah, okay, I see. So yeah, so this is obvious. So this shouldn't be language j, this should be first or second j, because we need the actual letter first. Okay. Hopefully that's it. Okay. What? False expected true. Oh, right. So this actually needs to be if language j is less. No, this is less than. So how is this false? Expected true. If second j. So let's print this again. Get these values. It's taking way too long on this one. Okay. So k is 11, q is 16. So this is language second j. Oh, right. Classic. Okay, this should be the same character. Okay, what do we do wrong now? H and L. Interesting. Okay, let's just print J here, where it breaks. Okay, we don't need to print this. So the first one is shorter, so that's fine. So let's print J. Okay, so we are at character 4. How are we at character 4? Oh, I see. So we need one other case. Yeah, we need one other case. So if language first, yeah, so we forgot one case. At first, J is less than language second J, then we just continue here. Okay, because then that already makes it. Okay, what the heck? Oh, sorry, we don't, yeah. Okay, this is way too many years. So we break. There we go. Okay, yeah, because if the first letter is less than, then we don't need to check anymore. Okay, you're given, okay, grids are recorded, okay, surrounded by water, okay, determine the perimeter of the island. So for something to be in the perimeter, it needs to connect to water or be outside the grid. Okay, so need to do that. Grid. Okay, when grid 0, and then we just have some kind of res here, and we have directions as usual for checking every single way. So 0, 1. Yeah, it's definitely tough to do these problems without making mistakes if you're doing them quickly. Like if I had like 10 minutes for a problem or something, it would definitely make a lot less, but it's still good practice, I think. Okay, so this is equals, and then we just have a nested for loop, right? So row and range rows for column and range columns. Now we need to check if it's land, then we need to check all directions. So if grid row column equals, what's land here? 1. yeah, then we need to do another loop. So for directions, new direction, or new row. This is the same as I have in a lot of my other videos. So row plus directions 0, column plus directions 1, and then if new row is less than 0, that's fine, or new row. All of these cases would give you another point, so new row is greater than or equal to rows, or new column is less than 0, or new column. It's going to get a little lengthy, but that's okay. Greater than or equal to columns, or it's water, it's fine too, right? So for grid, new column equals 0. Okay, actually, whatever. Oh, that's fine. Okay. So if that's the case, then we need to add 1 to our res because that's a perimeter, and then we just return res here. Okay. Oh, what the? Okay. Oh, I see. So it's giving me a problem here because this is too long. Okay, fine. So probably want to do this or this or that or that. Oh, I see. So this needs to be or that. There we go. No more complaining. More complaining. So this should be direction. Okay. Really more complaining. New row. Okay, there's off. Alright. Come on, stop complaining. Thank you. Okay. Last stone weight, you're given an array of stones, where stone I is the weight of the stone you're playing game with X stones. On each turn we choose the 2 heaviest. Okay, result, stones destroyed. Okay, at the end, alright. Okay, so we'll just use a heap here. Heap equals, we can even just use stones directly, I think. So stones, yeah, let's just do stones directly. So heapify. We do want to do one more thing actually, so let's do this instead. Stones. Let's actually make a new heap. So we can have negative numbers, so we can get the biggest. So heap dot append times -1. Stones, yeah. So now we do heapify heap. Okay. And then we just keep hopping from stones until this. So while length heap is greater than 1. Yep, so first equals heap hop heap. Second equals heap hop heap. And then we have to multiply them times -1, so let's do that. So these are the 2 stones, and then we just have to see which one is bigger. So I think, yeah, okay. So if second is greater than first, then we heap push heap second minus first times -1. We just push the difference. Okay, if first is greater than second, then we heap push heap the opposite. Okay. Alright. Okay, and then the last case they're the same, so we don't do anything. We don't need to add to the heap. And then we just check if there's either a 1 stone or no stone. So if heap return heap 0 times -1, else we return 0. Okay, don't tell me oh wow, amazing, no mistakes. Kth largest element is stream. The turn class, notice kth largest element, not the kth distinct. Okay, pretty straightforward, I think. So what we're going to do is we're going to make a heap, and it's going to be a size k. Yeah. So let's do that. So self.heap equals this. Then we are going to self.k, or we're going to need to store that value, equals k. So for num, in nums, we are actually going to yeah, so we're actually going to push every element onto the heap, and then we're going to pop until we have k elements. So heap push heap num while lang self.heap is greater than k, heap pop heap. So that'll give us the right size. Now when we add, so we do a heap push val onto the heap. Okay, and returns element. Okay, so we heap push it. Now we pop, yeah, so if length of self.heap is greater than k, heap pop heap, and then our kth largest should just be the min element here, so return self.heap 0, so this needs to be self.heap self k self that needs to be that. Okay, cool. Construct string from binary tree. Okay, so we're gonna have, what would it see? Given a root of binary, construct string per parentheses and integers, pre-order traversal, and return it with empty parentheses and not fuck. Okay, so let's see. So one, okay, so there's a parenthesis anytime you have new nodes. Okay, so 1, 2, 4, and then you have this other node. Sure. Okay, and then here 1, 2. Okay, so when there is no left and there's a right, we need to have this empty parenthesis. But if there's no left or right, then we don't need those, I think. And if there's a left and no right, we don't need those either. Okay, so let's just have a res here. And it's just going to be a list, and then we're going to return. So def, and we're going to do a tree traversal. So first case, if not node, we don't do anything. Otherwise, so we need to push the value of the node onto the rest. So append node.val, and we're going to want to append it string-wise. I might cut out for a second there. So we're going to append the value of the node. Now we need to see if there are no left and right children, we can just return straight away. So if not node.left and not node.right, return straight away. Okay, now if there is no node left and there is a node.right, then we need to have a open and close paren. So let's do that too. So if not node.left and node.right, res.append. So we need to append. We can technically just append this together. I believe it shouldn't matter because we're going to be joining the whole thing anyway. So if the string is more than one character, it's fine. Okay. Now what we need to do is we need to append the node.right, right? So what we can actually do is we can even do this, and then we call the helper function on node.right. So okay, now we append this. We might have a little bit of repeated work because I'm just trying to do this fast, but that's okay. Okay, next, if node.left and not node.write, then we just do append. So yeah, we can definitely clean this up maybe later. Okay, so if that's the case, we do node.left. And then we do, actually this shouldn't matter, so this should just be, if not node, yeah, so this should always be node.left actually. Yeah, so we can just do that. Okay, oh, by the way, we do want to return in this case. Okay, so there should always be a left now, I believe. Yeah, so let's just do that here. Append. So we want to append this. Then we call node.left. Okay, then we append this. Okay, now we need to do if node.write. So res.append. An open parenthesis again. Call node.write. So here. Okay, and then we can res.append. Close parenthesis. Okay, and then we can just return here. So now we just call helper root, return, same kind of thing. Hopefully that worked. So what's our issue? Oh, right. So we don't need to return res, we need to actually join this whole list, so. Cool. Hopefully that works. Nice. Okay, so let's go over these now with some time and space complexity. Okay, so +1 is pretty straightforward. So all we're doing is we have some array. And then we start, so the way addition usually works is you have a CIN and then you have a result. So basically all we're doing is we have a CIN of 1 and we're just adding 1 over here. And then if our result is 10, that means we need to have a carry bit and go to the next one. So we need to have a carry 1, make this 0. But if our result here is anything other than a 10, we can just change it directly, right? So if this is a 3, we just put in a 4 and then we're done. And then we have one other check where if we have something like this, right, I think. So if we add 1, this would be 0, this would be 0, this would be 0. So we have one other check if our CIN at the end is a 1 and we have to append it. So that's pretty straightforward. Happy number is also, let's actually do the time and space complexity here. Space. So this is just going to go through our digits one time and our space. We're not making anything else, so 1. Happy number, so we are taking the digits and we are multiplying them. We're not multiplying them, sorry. We are getting the square of each digit and then multiplying them. So we just have some new number here and then we have this 19 and all we're doing is we're just, every time you want to get the last number, you just mod it by 10. So if you mod 19 by 10, you get 9, square it, add it to this. So this number will be 81. And then to pop off the digit, you just divide by 10. So if you divide by 10 with this in Python, it'll convert it to an integer and divide by 10. So then we'll have 1 and then we'll just do +1 squared. And then we get the new number and we just replace it. And then all we're doing is we have a visited set to make sure that we haven't seen this number before. And if the number is 1 also, that's our condition. It says if it's 1, then it returns true. So it's pretty straightforward. Time. It's hard to say what the time will be, like how many times this will go before it loops. I'm honestly not sure. I want to say something like n, but I'm not exactly sure of how this would look. I would have to look at this for different numbers. Because you can get numbers that are bigger, right? So you have 68 that goes to 100. But I'd say it's roughly time n. Because it's not like 68 will go to like 10,000 or something, I think. And then space, 1, we're not making anything new. Meeting rooms. Okay, so all you're doing is you need to be sorting the intervals, and then when you sort the intervals, it's pretty straightforward. So I think this first case, they are sorted, but you need to sort them to make sure that they're in order, and then you can check. So if you have like this, 0, 30, 5, 10, 15, 20. So these are the times that that all the meetings are, and all you're checking is check the last number of this and the first number of this, and then it has to be the last number here has to be less than or equal to the first number here, right? So if this meeting is 0 to 30 and this meeting starts at 5, then you can't attend both. So this starting would have to be 30 or greater. So you're just checking every single one like this, and if every time the second digit here is less than or equal to the second digit here, or the first digit here, then it's true. Otherwise, whenever you find a case where that's not the case, you can just return false. So for time and space complexity, time is going to be n log n because we needed to sort the intervals, and space is going to be O1. Okay. Min cost climbing stairs. So I don't want to go too much into this. This is basically like a house robber where you have two cases, and so the cost. So the optimal solution here, just to look at it really quickly, is like, let's say we have this 10, 15, 20. And so you have to pay the cost and you have to climb one or two steps. And so if you just think about it, the cost of the last two steps is what? So the cost here is 20 and the cost here is 15, right? Because we can do 15 and we can go up two steps. So then the recursive relation is the number before these is just going to always be the cost of this, right? So it's going to be cost of I. And then we can either go here or here. So if we have these values, if we have what these costs are, we just take the minimum. So here it would be like 10 plus 15. And so that's why the output would be 15, because the cost here is 15. And so on, right? So if the cost here at this value was 25, let's say, right? That's the smallest. Then what's the cost at, let's say we have some value 8. It would be 8 plus, we can go 1 or 2. So it would be 8 plus the minimum of 25 and 15, which makes sense. Then that would be 23. So the cost from this stair, and then you do so on all the way till the first stair, and then so then you don't do the first stair, you check which one's smaller, the first stair. Once you recurse down these, this first will actually be the first stair, and last will be the second stair, and you just take the minimum. And so here, and yeah, this is pretty much like house robber. So if you have any questions on this, I have like a 40-minute video on extensive house robber analysis for all of these solutions. So this is just going to be a big O of n space big O of 1. So climbing stairs is kind of similar, except there's a slight difference. Before, these two actually had values, but now when n equals 3, we're on the last stair, so the number of ways we can climb up once we're at the last stair is actually 0, and when we're at the second to last stair, so let me draw this real quick. So if n, so this is 3, 2, 1, 0 for this example, for n equals 3. So when we're at stair number 3, there are no more ways to reach the top because we're already there. So the value here is 0. Then when we're at stair 2, the only way to reach the top is go up one stair. And so these are our base cases, but actually instead of using these two as my base cases, I use these two as my base cases. Because the problem is the recurrence relation doesn't work if you use these two. So the cost at the second to last stair, the number of ways to reach the second to last stair is going to be 2, right? We can either go 1 or 2. And so these are the two stairs you care about. The stair right before the top and the two stairs before the top. And then for the recurrence relation, the number here is going to be the number here plus the number here, right? We can either take 1, or we can take 2. And so whatever the ways at n are going to be ways at n plus 1 plus ways n plus 2. And so you can see that's true for this case, right? So for here, it would be 2 plus 1, which would be 3. Because the two decisions you're allowed to make is you take one stair and you take another stair, so that's 2 decisions. And then from there, you just add these up. So it's just that. Okay, and you can try this. You can try this for a bigger n value to prove to yourself that works. Okay, verifying L&E dictionary sets, also pretty straightforward. I did screw up a few times here. And so the first thing you're going to want to do is you're going to want to have a hash map of every letter. So let's just call this letter L, and then its index in this order. And so the smaller index means it's comes earlier in their alphabet, right? Like, let's pretend this alphabet instead of this was, the normal alphabet, A, B, C, D, whatever. And so the index of the letter the smaller index means it comes first in the alphabet. So there's a couple of edge cases you have to look for. One of the edge cases is they show it to you here, this apple and app. And so if all of the letters that you're looking at are equal, but then you run out of letters in the second word, that becomes invalid, right? Because think about in the English language, like if you have a word like a, and then you have a word like an. So a is going to come before an, right? So if you have an and a, that wouldn't work because the empty space always comes before a letter. And so you have to check every two words, word by word, to make sure that they follow the lexicographically correct order. And so what you do, like let's say you have like this, bad and then banned, and there's a couple cases. So you check letter by letter. If they are the same, then you need to check the next letter, right? Because you need to know more. So if they're the same, you check the next letter, and then you check this D, and then you check this N. As soon as the letter from the first word is smaller than the letter from the second word, we don't actually need to check down, so that's why I screwed up at. So that's going to be right here. As soon as you have one letter of the first word smaller than a letter from the second word, you're done, because that does mean that this word comes first. Then vice versa, let's say you had this, right, ban versus bad, and these are the same, now you come here. So as soon as one letter from the first word is bigger than a letter from the second word, then it's also false. And that's what I did here. So just return false. And if that's not the case, then you keep going. So that would be the last case, is they're equal. Then you keep checking until you run out of letters in the first word. And if you run out of letters in the second word before you run out of letters in the first word, then it's invalid, because that would be like this apple and app. So if they're all the same, the first word has to run out first. Okay. Island perimeter is really straightforward as well. Oh, by the way, let's check. Yeah, so let's do the time and space for this one. So time is going to be big O of n, because we are just recursing back space of 1. We don't have an array. That's the optimal solution. Verifying this alien dictionary is time. So we need to go through this whole order array, so whatever that is. So let's just call that 26, all right? There can only be 26 letters max. And then we need to check every two words, and we need to compare every single character in the word. So let's call word or something. So by the way, this 26 is going to run down to constant time. So let's just say that W is the length of the longest word, and then there are n words. And so that would be the case where it would be O like this, because you're comparing n words and you're comparing character by character. So that would be n squared solution. And then space. We make a dictionary of letters, but like I said, that's going to be O of 26, which should just round down to O of 1. Okay. So yeah, so island perimeter, pretty straightforward. So all you're doing is, let's just say we have this box, and let's just say we have some islands, right? So whatever. Probably actually even, that's fine. Okay, so let's say our islands are 1s, and then our water is 0. So if you have some 1s here, whatever. So it should be a connected island, right? So like this. So let's say this is a connected island. All you're doing for the perimeter, as you can see, these lines are, you have a line anytime that if you go in that direction, you're going to be out of bounds, right? So like this would be a line, or sorry, this would be a line, because so we need to be on land, and then if we go in that direction, we're out of bounds. That would add to the perimeter. And the other case is when you go in that direction, you go into water, right? So like here, you would go into water. So if this is a water, then this would also be a 1. So all you're doing here is you're actually just, you have a nested for loop, and then anytime you find a spot of land, you just check in every direction and you ask yourself, is it out of bounds? In that case, add 1. Is it water? In that case, add 1. And if it's an island, then you don't add anything, right? So like if you're in this box and you check this does not add to the perimeter. So that's pretty straightforward, and this is all you do. You just say, you make a new row and a new column, and you just say, is it out of bounds, which is these, and then if it's 0, then it's water. So pretty straightforward there. Time is going to be O of, so this grid is row by column. We're checking every single one, and then there's 4 directions, so it'd be 4 times row times column, but that's 4. We can get rid of the 4. Space we have a directions array, but that's just O4, so that doesn't go to anywhere. And I think, and we have a res, but that's a constant value, so that's O1. Okay, last stone weight, pretty straightforward. So we have a bunch of stones, right? And they're going to be ordered here, actually. And the way we're going to do this is we're going to take all these values and make them negative, and then we're going to have a min heap. So remember, a min heap, the smallest value is going to be the biggest negative value, so it'll be ordered like this. -4, -2, -1, -1. So we're taking every stone, we're making the value negative, we're putting them into a min heap. And then we're saying while the size of this heap is more than 1, meaning we have more than one stone, we just pop 2 stones. So let's say we pop this 8 and 7, we make them positive, and then we figure out whichever one's bigger and we push in the difference. So actually what you could do is you can just, if you want a one-liner here, what you could do instead of all this is you can literally just say this: if absolute value of first minus second does not equal 0, then we can push it in. And that would work as well. So this thing right here, I think that should technically work. Alright, heap. Okay, so that didn't work. So interesting, actually. Output -1. So why doesn't that work? Let's see. If absolute value of first minus second does not equal 0, then we push it in. It should be fine, I think. Am I screwing up something really obvious again? I think so. Oh, right. So we have to push in the negative value. Okay, there we go. Yeah, so that would be a one-liner if you want. So you're literally just taking the difference of whatever you pop. If it's non-zero, then you push it in, and you push it in negative, because then you're gonna want to keep pushing them in negative, so then you can always get the biggest. So let's, like, this would happen. Then you're gonna put in a -1, and then what would happen? So we're gonna take this -4 and -2. So we're gonna pop those. So we have 3 -1s. We're gonna pop those. The difference would be 2. So we're gonna put in a -2. Then we're going to have -2 and -1, which would be -1. Then we have these 3 -1s, so you're going to pop these 2 -1s. They're going to cancel, and then you're going to have a -1, so your value should be 1. And that, yeah, so that's just, so that works for that. Okay. And time and space. So for, let's see. I think technically we should be able to have n heap pushes and heap pops, so I think that would be n log n. Heapify is big O of 1, but I think for these you can technically have n heap pushes and heap pops. So that's n log n, and then space is going to be n because we can have n stones in the heap. Okay, kth largest element in stream is also a little bit of a neat solution, and so let's say you have like actually we can go through this example with our heap. So k is 3, and then you have 4 elements. So what we're going to do is, once again, this time we're going to push them in just normally. So we're going to go to, and then whatever's in the end doesn't matter, right? Because it's a heap, so it's only the smallest element that matters. So all we're doing is we're pushing in every single element into the heap, and then we're saying while the size of this heap is bigger than k, pop to get it down to what we want it to be. And so we're going to pop one element out, and so our new heap, once it gets sorted, is going to be 4, and then these two can be in any order. So you could see that we can always get the k smallest element by having a heap, or kth largest element, by having a heap of size k, because this is the 3 largest elements. So if our heap has the 3 largest elements, the smallest of the 3 is going to be what we want. And so as soon as we pop the minimum, we can always get what we want. So let's just go through the solution. So first it wants to add 3, right? So when we add 3, we're going to add 3, and then we're going to pop 3, because we're going to always want to size it down to k. So we're going to add 3, we're going to pop the smallest, get rid of 3, and then our return is going to be 4, because that's the min value that we have. Then we try to add 5. So let's add 5. So we add 5. Smallest value is going to be 4, so we're going to pop that. Now our smallest value is 5, so then our output will be 5. Okay, add 10. So we add 10. Smallest value is going to be 5. Pop that. Now our smallest value in the heap is going to be 5, so we're returning 5, just like it does. Now we add 9, so let's add 9. Smallest value is 5, so now our smallest value is 8, so we're going to return that. Then we add 4, and A4 will be the smallest value, so it's going to get popped, so we add it, we pop it again, and it'll be 8 again. So hopefully that makes sense to how to get the smallest value there. As far as time, it's going to be, so to make the heap, we pushed, it's going to be n log n. We can definitely make this, can we make it more efficient? Probably. No, actually no, because so we can push n log n times, or we can just put in numbers heapify, but then we're gonna have to pop a bunch. So either way, it'll be n log n, and then every add operation will be a push and a pop. So every add operation will be time log n, because we're gonna at the most pop one value. So that'll be log n. First one will be n log n, and space is going to be O of however many elements we have in the heap. So whatever the max number we have at one time. Okay. And then construct string from binary tree is also pretty straightforward. So we just have, instead of construct string, imagine we're just constructing like this is kind of like a traversal, right? Like when we did a post order traversal or an int order traversal where we had some array. This string is pretty much the same thing, except now we have parentheses. So we are on, like, let's look at this example of 1, 2, 1, 2, and then we'll look at the other example, 3, 4. Let's make this bigger. So we just traverse. So we're here, and so we put in the value. And the reason we want to have a list instead of a string is because in Python, if you just do like string plus something, you're actually making a new string. So that's going to be big O of n time, where n is the length of the string, where a list you can just append one element, and that's going to be big O of 1 time. So anyway, so we're going to have 1, and remember all these are going to be strings, so just know that this one we're putting it as a string. Okay, now we check, does it have a left? Yes, it does. Okay, have an open parenthesis, traverse down. Okay, and then this open, so comma. We have a value here, so 2. Do we have a left value? Yes. Open parenthesis, traverse down. Okay, put in 4. It doesn't have a left or a right, so we just return up here now. So now that we're done with the 4, we have a close parenthesis. And then we don't have a right, so we don't need to do anything there. So then we traverse up to the 1, we have a close parenthesis because we're done with the left. And now we do the right for the 1, so we have an open parenthesis, traverse down, put in a 3, and then traverse back up and do this. So this is the other one that is tricky. So let's do that. This 1, 2, 3, 4. So we have 1, and I'll just show you the tricky part, I guess, and then we're not going to do the whole thing. But so let's say we're actually here. So we are going to be putting in this value of 2, and now we're going to, but what we don't want to do, so actually for this, yeah, so for this, you would want to have a left. So this is the tricky part, is you need to have a left and a right. And so if you just did this, like if you just said, if there is no left, do nothing, and then for the right, do this, then you can't really tell if you have a left or a right, right? Like this would be the same. So you'd have 2, 4, and you wouldn't know, is this 4 the left or the right? So they're saying whenever you don't have a left and you do have a right, then just put in these 2 parentheses. But then if you do have a left and you don't have a right, then put in whatever your left is, and you don't need extra parentheses for the right. And if you don't have either, you don't need any extra parentheses. So that's the only trick, is when you don't have a left and you do have a right, put in these 2 extra parentheses. Okay, and then as far as time, so we are going to traverse down every single node, right? So that's going to be big O of n and space. If you don't count res, it's going to be big O of 1. And if you do count res, we're going to put in the value of every single node. So that's going to be big O of n. And we're going to have parentheses for every single node, but that rounds to 0 because that's just going to be like n times 2 or n times 3 or whatever, which is irrelevant. Okay, so I hope you like this video. And if you do, like and subscribe. It helps grow the channel. And I'll see you in the next one.